Hello, welcome to another video of heuristic algorithms. In this video we're going to discuss hill climbing methods, and for that purpose we're going to work on an example. Let's consider the function described here as a function of x and y. It's a quadratic function with terms with x squared, y squared, and xy, as well as a linear terms just with x and y. And we can solve the problem of finding the maximum of this function using calculus by computing the partial derivative of z with respect to x and the partial derivative of y with respect to x, making those equal to 0, and then solving the set of equations that come out of that. And the solution would be readily computable as x equals 10 divided by 19 and y equals 43 divided by 38, and that would be the point with the highest point of the function. The challenge many times is that the functions that we work with after we solve the partial derivatives are not easy to find or to extract the point when they meet, and sometimes it's easier to do this by means of numerical computations. In this example, we're going to try to find the maximum point, or the optimal value, if we try to maximize this function z by a hill climbing method. And the way we do this is we start in any point and then we explore the neighborhood around it. The definition of the neighborhood depends on the problem, and the way that I do it here is not by far the only way that we could approach this. But the way that I'm defining the neighborhood is from the current position that we have. We defined a step both in terms of y and x, and then we either move orthogonally into the four corners of a square, so to speak, in which we move both in in x and y, this size of the step, or we go in the negative sides both in y and x, or a combination of negative x and positive y, or positive x and negative y. So if you look at it from if it was a point and then a square around it, we're advancing diagonally in any one of these directions. Of course, we can define other ways to move around this neighborhood. We can go just moving exclusively in x or exclusively in y, either in a positive or negative way. But that's how I define it here. And let's say I have here prepared a spreadsheet that contains the two initial points. I have 0 and 0, and these are going to be the two cells I'm going to use for input the information. I'm going to highlight them in yellow. And then this is the evaluation of the equation. All I'm doing is, as you can see, multiplying x squared and times -5 and so on. Naturally, at 0, 0, the value of that expression is 12, because that's just the coefficient that we have there, 12. And then I am defining steps at this moment for x of 0.1 and for b of 0.1, and those steps help me to figure out which are the new positions I'm going to work with. This would be 0.1 or -0.1 in x, and 0.1 and -0.1 in y. So these are my 2 points I have coded here. If I use the first and third combination of what x plus a and y plus b would be, or 1 x plus a, and y minus b with b, and so on and so forth. And here all I did is copy the same formula down, so I'm recalculating this whole spreadsheet. And these, or not the whole spreadsheet, the same formula using these few points. And of course, you see we are exploring the neighborhood in these four corners, and the highest point is out of these four positions is 1303, and that would be the one that we need to use next time. So that's exactly what I do, and I select 0.1 and 0.1, and again everything is recomputed. The next one that I find to be the best one is again 0.2 and 0.2, so I go to 0.2 and 0.2. Of course, these would have to be done in a computer program to work it faster. And still, the best one that I can get is 14.67 with 0.3 and 0.3, so I go to 0.3 and 0.3. Still, the best one is 0.4 and 0.4. Still the best one, well, here it might be that we have the same values. Here we need to see more digits to make a decision, and it's actually the same, so it doesn't matter if we choose to go 0.5 and 0.5 or 0.3, 0.5. So I'm just gonna go in the same direction, and we're still improving. 0.5 and 0.5, and from that point now it becomes evident that I'm better off going in this direction. 0.4 and 0.6, 0.4 and 0.6, and now I'm getting better at 0.5 and 0.7. And I'm getting better at 0.4 and 0.8. And now 0.5 and 0.9. And now again I get a break, so it doesn't matter if I go either way. So I'm going to just go 0.6 and 1, and now it's better to go 0.5 and 1.1. But again, what we're doing is we're exploring the neighborhood, and we're taking the best that we find in that neighborhood. 0.6, 1.2, and we can't keep going in this way. Let's see, 0.5, 1.3 is the best. Now is 0.6 and 1.2, but I think we already went there, 0.6 and 1.2. So now this is gonna keep us in a loop. So somehow in between these points is the best solution. So maybe what we could do is we can define a smaller step to have a better approximation to the optimal solution. So I changed my step, and this is an important way of approximating the right solution. So now the steps are 0.5, and I can decide better that I'm better at 0.55 and 1.25. So I exactly do that, 0.55 and 1.25. And here I can see that I'm better at 0.6 and 1.2. and we visited this place before. So still we're somewhere in between. This is the optimal solution. We can go even further in our definition, maybe like that. And now it's clear that we're better off now with 0.59, 1.29. This is a direction that we have not explored before. So we're going 0.59 and 1.19. And it suggested we keep going in that direction, 0.58, 1.18, and still in the same direction, 0.57, 1.17, and we're still making progress because the current value is 17.3037, and if we take this value, it's going to be 17.308. So we're still making progress. 0.56, 1.16, still in the same direction. 0.55, 1.15, and it's getting closer and closer. 0.54, 1.14. We're still improving at 17.3157. It's still the best solution. 0.53, 1.13. We have now a tie here for the maximum, and we're still improving just a little bit. 31.57. No, we're not actually improving. This one is better. This one is the best we have so far. Okay, we could probably improve if we reduce the step size even more. So we see this might be an improvement. We need to add a number of digits here. Yeah, with this still an improvement, and we will go with 52.9, 139. 0.529, 1.131, and that gets us to 57, and we keep going in that direction. And from this moment on, it's a matter of how far you want to go. The values, the optimal values that we find using calculus were 10 divided by 19 and 43 divided by 38, and as you see, we are moving in the right direction, but it will take us to do this many times more, but the computer can do that way faster, and a smart selection of the step would take us there faster as well, because we can start with a larger step and approach the solution faster. I'm going to talk about more of these in the next video.